Well, welcome and good afternoon. We've got kind of a fun little arrangement here. We're running my computer for the audio and the video, and we're running John's computer for the slide deck. So bear with us. We'll maybe tune this up a little bit as we go. But for folks that don't know, Burlington is BED is Burlington's municipal electric utility. And my name is Brian Riley. My department, Energy Services, serves as the city's EEU, Energy Efficiency Utility. We also support the department in the city's 2030 vision, which includes eliminating fossil fuel usage in the thermal sector. So we offer tech support and incentive programs to that end. Around 2018, we launched what we call post-install incentives for ductless mini splits, centrally ducted heat pumps, and air-to-water heat pumps. Since then, we've supported the installation of over 1,100 mini splits, 350 centrally ducted heat pumps, and one air-to-water heat pump system. So we estimate about 60 to 70% of the city heats with boilers, hydronic heat. This year, we've seen several renovation projects that seemed like ideal candidates for air-to-water heat pumps. The owners pay the utilities. There's existing central gas boilers and the desire for cooling and better control of the heat. In our attempt to promote the air-to-water heat pump, it was clear that very little has changed in Burlington since that first air-to-water install in 2018. So we reached out to John to understand why and to find out where the opportunities lie. Many of you are familiar with his work. In 2018, John supported Efficiency Vermont's Air-to-Water Heat Pump Summit. He's also a past presenter at Better Buildings by Design. In May of 2026, John will present a session at Better Buildings titled Heat Pumps, Hydronics, and Thermal Storage. Tomorrow, we will visit several city and Champlain College facilities to gauge the feasibility of integrating air-to-water heat pumps. So welcome. Before we hand it over to John, some general info. We plan to break around 2 for 10 minutes, and then feel free to place questions in the chat. We'll try to answer those real time. If we can't, we'll certainly follow up with you. We'll send a link to the recording, and we'll also include a survey in that email. In the survey, we will try to gauge interest in a air-to-water summit for this winter. So, all right, John, you want to take it over?
Good to go. Thanks, Brian, and thank you folks for inviting me up here. I love coming up to Burlington. Had a beautiful drive up through the Hydronics this morning. And we're going to talk about air-to-water heat pumps. So for the first hour, we're going to talk kind of in general terms about what they are, how they operate, what the market looks like, both in North America as well as a very established market in Europe and Asia. And as Brian was saying, we'll take a short break, and then we're going to get a little more into the weeds on the technical side of how do you take an air-to-water heat pump and retrofit it to an existing hydronic system that likely has a boiler as its heat source. Certainly with this size group, I'm wide open to questions as we go. Don't hesitate to ask questions as we're proceeding through here. And I guess, Brian, you monitor the questions on the chat?
I will try to without having my
so
face in there.
Here's kind of our informal agenda. What is an air-to-water heat pump? How does it operate? I'm going to show you some results of performance simulations. About 3 years ago, we worked on a project for NYSERDA where they wanted to compare air-to-water heat pump performance to air-to-air systems or to geothermal heat pump systems. And we did it, but our database of weather is just for New York State because it was for NYSERDA. But we do have Burlington. We have Plattsburgh right across from Burlington. So cold climate, obviously, and I want to show you what the simulations look like for performance in terms of seasonal COP and a percent of the space heating and domestic hot water load that the heat pump can carry. And then talk about at least why I think the North American market is very well positioned right now for major growth with air-to-water heat pump systems. Then after the break, as I say, we'll talk about existing hydronic systems. I think the majority of the initial air-to-water heat pump placements are going to go into existing hydronic systems with a boiler. And there are many reasons to keep the boiler in the system and have it as a dual fuel system. It's not essential, but there are some positive reasons for doing that. Heat source piping arrangements. We're going to talk technically, how do you put that heat pump in there in terms of schematics? And then I'll show you some example systems. And put this slide in just to give you my background. My dad was a carpenter. I grew up in construction. Went to RPI, got a degree in mechanical engineering. And in 1983, we formed Appropriate Designs. And at that point, we were designing low energy homes. Some of you remember back then, that's very thick walls and, mega amounts of insulation in these buildings. And we've moved more into designing hydronic systems over the years. So we specialize in hydronic systems. I actually lost count how many systems we've designed. We've done a lot of residential, both common residential, high-end residential, light commercial systems. I wrote a textbook. It's in its 4th edition now on hydronic heating. I brought a copy with me. It's out in my truck. If anybody wants to look at it, I can certainly grab it for you. And we developed some online training programs through HeatSpring. Anybody here work with HeatSpring on training? They've got a lot of online training programs in renewable energy and other energy-related topics. Okay, so I always like to start off with this. If you're wanting to work with an air-to-water heat pump, it's important to understand what I'll call Hydronics 101. And over the years, and I've been doing this for about 45 years now, what I've seen over the years as solar thermal came into the market, pellet boilers came into the market, geothermal heat pumps came into the market. What I've noticed that's kind of a common thread is that people get very excited about that new heat source. And if it's going to work with a hydronic system, they simply assume that I just cut 2 pipes, remove the boiler, put this new magic box in place, connect those 2 pipes back up and turn it on, and everything will be great. What do you think? It's got to work as a system. And the analogy I use sometimes is if you were going to get into NASCAR racing, here's the plan. We're going to go to Italy. We're going to buy a Ferrari racing engine for $500,000. Beautiful piece of hardware. We're going to bring it back. We're going to install it in our Cub Cadet lawn tractor. And then we're going to put that on a trailer and take it to NASCAR race. What do you think? See, you want to see that, right? Yeah. It's a bad mismatch between a very highly efficient and capable energy source and what we call balance of system, the transmission, the wheels, and everything else. And we want to keep that in mind. If you're going to put an air-to-water heat pump system into an air-to-water heat pump into an existing hydronic system, you need to evaluate that system. And quite honestly, North America is kind of the Wild West when it comes to hydronics. There's a lot of systems that don't really fit into a standard piping configuration. There's about half a dozen standard piping configurations, but then you'll see things that over the years, they've been cobbed up by different contractors, just different ideas, and you've created this system that nobody really wants to deal with anymore, unfortunately. So it is important to understand hydronics. And, here's some examples. I mean, this is PEX tubing stapled up to the bottom of a subfloor. No heat transfer plates, no insulation. This is a do-it-yourself project. That's actually not a boiler. That's a tankless water heater. Oh my goodness. And if you look really close right here, that's an expansion tank and it's being held up by some Romex cable that's been lashed onto it. Over here, this is where they ran out of aluminum plates and they started to use Reynolds wrap. Okay, and then this picture over here, I've often asked, what do you think this gentleman is doing right here? Praying. He is praying. That's the correct answer. Because look, we've got a lot of hardware here, and there's nothing wrong with that hardware. The controls, the zone valves, the pumps, those are all major brands. Been around. Everything from a hardware standpoint is good, but look at how it's put together. And imagine yourself walking into that mechanical room at 2 a.m. because something isn't working, and you're the tech that's on call to fix it, and you're looking at this. And you're thinking, how is this supposed to work when it's working correctly, much less what's wrong with it? So it is important to understand hydronics before you get involved with designing any type of heat source into that, be it an air-to-water heat pump, a geothermal heat pump, even a modern boiler. Right? So just putting a new heat source in isn't going to fix that existing situation. Now, to get into air to water heat pumps specifically, I call it a rapidly growing approach for electrifying hydronic systems. Most hydronic systems today, I don't have the exact number, but I would wager it's upwards of 97, 98%. The hydronic systems in North America are running on a fossil fuel boiler of some type. Probably natural gas would be the dominant, then fuel oil, propane. There are some biomass boiler systems. I know up here in Vermont, you've got some activity in that area. And there have been some systems, gosh, going back 25, even 30 years ago, where there were early adopters working with geothermal water-to-water heat pump systems. But because the primary market has been fossil fuel boilers, and we look at how do we electrify an existing fossil fuel-based hydronic systems? Well, basically, you could go to an electric boiler. Depending on electric rates, that might be feasible. I was up in Quebec a few weeks ago. They're paying 6 cents a kilowatt hour up there. So it may be a feasible competitive energy choice against gas or against oil. But in other areas where electricity is upwards of 40 cents a kilowatt hour, an electric boiler will work, but it's very expensive to operate it. So if we put that one aside, we come down to heat pumps. And basically there's water to water heat pumps, mostly tied to geothermal earth loops, or there's air to water. We've designed several geothermal systems over the years. They work. The difficulty with geothermal is the site and the expense. Not every site has the land area or just the, primarily land area, but outside the building, can we install an adequate earth loop? If we were doing this in a suburb on quarter-acre lots, it's going to have to be a vertical borehole, and that gets pretty expensive. Right now, upwards of $3,500 per ton in central New York, where I live, to do vertical borehole systems. So a 4-ton system, before you even get inside the building, you're at $14,000 just to get that earth loop in place. And yes, the geothermal systems do have a slight efficiency advantage over typical air to water. And that gap, though, is closing. It's closed significantly over the last 20 years with evolving air source heat pump technology. So air to water really, in my mind, is the premier option for bringing electrifying hydronic systems. And of course, not only are you electrifying the heating side, but when you buy an air to water heat pump, it comes with a reversing valve. So it's a chiller as well. So you have the option to use chilled water cooling. Now, I'm not going to go too far into that, but I will tell you, don't just start pumping chilled water through a radiant floor slab or baseboard or cast iron radiators. What's going to happen? Condensation. But a system can be engineered. You can use an air handler. You can use fan coils that have drip pans in them. It's possible to do it. We've done several systems where we've used chilled water from a heat pump to use cooling. And that air to water heat pump can also be used as the primary source for heating domestic hot water. Okay. So again, most North Americans are familiar with these ductless mini splits. We see these. I'm sure you're probably incentivizing them up here, as are many utilities and many federal government, state government programs. So people are familiar with air-to-air heat pumps today, primarily with ductless, but also central air-to-air. And of course, there's been a lot of interest in geothermal. And I'm still looking for this multicolored pipe to install it. I think it looks really nice under the grass there. But the concept of putting piping in the ground, either horizontal earth loops, vertical earth loops. So again, people they're familiar with that, but when it comes to air to water, this is the new kid in town, so to speak. This is the new technology. And yet, from a heat pump standpoint, if you understand a basic operation of a heat pump, how it absorbs low temperature heat from some source, amplifies that temperature through a vapor compression refrigeration cycle, and then delivers that energy to some other material. That's kind of a generic description of a heat pump. Well, an air to water heat pump is absorbing heat from outside air and it's delivering it to a stream of water or a mixture of water and antifreeze. And at that point, a hydronic distribution system of some sort is used to take that water or that mixture of water and antifreeze into the building and distribute it. So you can see up here, this is a space pack unit. It's fairly new. That's about 2 years old. You see the two insulated tubes on the side here. That's the inlet and outlet. There's an electrical cable out to it. And notice it's up on a stand. That's very important when we talk about installing these heat pumps. We don't want to set an air to water heat pump or really any outdoor equipment, especially in a climate like this, 3 or 4 inches above the ground on some kind of a plastic pad or a concrete pad. It's going to get snow in it. It's going to, you can see under here, you see how the ground is wet? It's not a leak in the heat pump. Anybody know why the ground is wet under the heat pump? Defrost cycle. All air source heat pumps need to periodically melt the frost that will form on their coils. And that meltwater simply drains out the bottom of the heat pump. If that's sitting low on the ground, and we've seen this happen, what will happen over a cold winter is you'll get this bathtub of ice forming around the bottom of the unit. And that ice will actually get up into the coil. And I've seen it crack the coil before. So you want to let that water drain out, and you don't want the unit sitting in snow. I mean, last winter, how was your winter up here last year, Brian? It was pretty tough. We had the worst winter in about 45 years in upstate New York. We had a ski area 7 miles from where I live had 300 inches of snow last winter. So the snow was literally, well, it actually would probably even be above that if somebody didn't go out there. But it is important to get the unit up off the ground. So I call it heat pump flavors: ductless or central, air to air, and then water to water. Again, that first word describes the source of the low temperature heat. The second word coming after two describes where the heat is going to go. So what we're doing with an air to water heat pump is we're borrowing the air side technology, the evaporator coil, the fan, so forth in the outside unit. And you can see some similarities between this. Okay, there's a coil back here, there's a fan, there's a grill up front, and it's a slightly different geometry there, but it's a similar physical concept. And then we're delivering it to the water side the same as a water to water heat pump. In fact, most of the schematics that I'll show you later today, you could use those with water to water geothermal heat pumps. The balance of the system doesn't really care what produced that warm water. All right. So just an overview of what's going on globally with air to water heat pump technology. This is a journal that comes from Japan. It's called JARNS. It's kind of the Japanese equivalent of our publication, the Air Conditioning, Heating, and Refrigeration News. And every year they put out an update. I don't have the update for 2024 yet. So the stats that I'm going to show you are based on 2023. But the global market for air to water heat pumps went up almost 22% over 2022, almost 5 million air to water heat pumps globally. So where are they all going? Well, a huge amount of them are going into China, and another huge amount are going into the European market. The European market is upwards of 90% hydronically heated buildings. So it's always been a very strong market for any type of hydronic hardware. And that just shows the market growth there. The red bars are China, just China. Everybody else is lumped into the purple and the blue bars and so forth. And if you're looking for North America, it's purple. It's a little tiny bar right down here. So I don't know how many air to water heat pumps were installed in, let's say, last year in the United States. If I had to guess, perhaps 1,000 to 1,500 units, something like that. That's going to grow, though. So again, what's happening? China was over 2 million units. Japan, almost 500,000 units. And then the major economies in Europe, France, Germany, UK, European market reached 1.7. There are incentive programs in Europe, directives as they're called. Yeah, right.
Are these systems all electric or are these like hybrid or dual fuel?
Well, the heat pumps are all electric, but they may be going into a system that has a boiler.
Okay.
So, honestly, I don't know. These are just sales for air to water.
Okay.
It doesn't specify what systems, if they're going in as standalone or if they're going in as retrofits.
And I had a question from MK. He says, can you retrofit an existing forced air heating system based on propane with air to water heat pump?
You could, yeah, you could put a coil in the air handler and go to that coil with the fluid from the heat pump. So yes, you could retrofit that. That's actually a really good question. The question about could I use an air to water heat pump in a forced air delivery system? The answer is yes, you could. I would tell you, what else are you going to use that air to water heat pump for before you make that decision? If you're going to use it for domestic hot water heating, or if you might want to add some panel radiators, maybe you want to heat a basement room or something like that, something beyond just heating. And the reason I say that, you could also take a forced air delivery system and add just an air source heat pump to it, an air to air heat pump. That would actually be more efficient than using the air to water. So why would you use the air to water? Like I say, if you wanted to do domestic hot water heating in addition to space heating, or if you wanted to have the possibility of other small hydronic loads added in the future. It could be as simple, I want to put a towel warmer radiator in the bathroom, or want to do radiant floor heating in a kitchen. Or maybe 5 years from now, I might want to do an addition, and rather than run ductwork out there, I'll do that with hydronics. So the answer is yes, you can do it, but look at, why, how do you justify going air to water versus just air to air in a situation? So anyway, before I leave this, you can see, excuse me, the market is very strong in Asia and also in Europe. And, it's primarily because hydronics is a very big technology in both of those markets relative to the North American market, as well as directives that are in place. Now, physically, what's going on inside a heat pump? Any vapor compression heat pump is basically four primary devices. You've got the evaporator coil, where liquid refrigerant evaporates as it absorbs low temperature heat. You have the condenser heat exchanger. That's high temperature liquid refrigerant, high temperature gas turning into liquid refrigerant, hence the name condenser. That's where we're taking heat away from the refrigerant, putting it into whatever's going to carry it farther in the building. If it's an air to water heat pump, the condenser is right here. So you've got hot refrigerant gas coming in. As it condenses, it gives up its heat to that water, and then the water goes into the building. You've got the compressor that's taking low pressure, low temperature vapor refrigerant, compressing it, driving up the pressure, driving up the temperature. That's where we get the temperature lift in a heat pump cycle. And what am I leaving? Oh, the thermal expansion device of some sort. That's where we take the high pressure liquid refrigerant and drop its pressure, and we start the cycle over again. So as the cycle operates, the net effect of the cycle is we're absorbing low temperature heat. And sometimes people will ask, well, how cold can it be outside where the heat pump can still absorb heat? There are heat pumps that can work to minus 22 degrees Fahrenheit. Now, before you get too excited about that, they aren't very efficient at those temperatures. Their COPs, their coefficient of performance, isn't much better than electric resistance heat at that point, but they're still running. And the other thing that happens at those very low temperatures, their heating capacity drops off substantially. And we're gonna get to that in a minute. So fundamentally, an air to water heat pump is using the same type of heat pump refrigeration cycle than air to air or a water to water heat pump. It just uses different types of heat exchangers for the evaporator and for the condenser. And one last component I should mention right here, the reversing valve. There was a time in the market where you could buy heat pumps that were heating only. If you just wanted to heat domestic hot water, or if you just wanted to do space heating, there was no need to produce cooling. Today, that's essentially gone. It's like trying to find a car with a standard transmission today. Okay, you know, a new car with standard transmission. I don't know if you can even find that. But the reversing valve is pretty much standard in modern heat pumps. And what the reversing valve does is basically it changes the function of the evaporator coil and the condenser. It basically now it's absorbing heat from water here. So we're producing chilled water actually this way. And then it is through the compressor and through the temperature lift of the compressor. It sends the high temperature gas up here and we blow air across that and we take that heat and just dump it to the outside. Okay. So this would be the summer mode over here. This would be basically the heating mode over here. And the reversing valve, if you look at it, you'll see the reversing valve changes position to take the machine between heating and cooling. And that switchover can be done, typically takes about 3 minutes in a heat pump because there is a time delay. We don't immediately switch a compressor or vapor compression cycle from heating to cooling. There has to be some time for that refrigerant vapor to stabilize the pressure before we switch it. Now, what's going on in the market? If you look at these companies up here, this is as of mid 2025, this is my tally of the companies that are offering air to water heat pumps in the North American market right now. And I'm sure you recognize some of those names if you're at all involved with boilers or hydronic systems. Companies like Burnham, or under its name now, US Boiler, Viessmann, major, probably one of the biggest boiler manufacturers in the world, Weil McLean. Lochinvar just introduced an air to water heat pump this year. Actually, several companies last year and this year, traditional boiler companies have gone into the air to water heat pump market. And then there are the bigger players globally, companies like Daikin, see who else, Hitachi, Gree, okay. Nordic, that's a Canadian manufacturer. NTI is a boiler manufacturer up in Canada. They're now offering an air to water heat pump, Skybel Eltron. So again, there's a lot to choose from as far as product availability. It's not as if there's one company or two companies here and you have to take what they have to offer. And there's more coming. I can't give you details, but I could tell you there's some major global players that will be in the US market, very likely in early 2026. Right? And what do they look like? Well, there's this is an Enertech heat pump here. This is actually the only monoblock air to water heat pump manufactured in the US. Many of these heat pumps today are manufactured in Asia. Some are coming out of Europe. Space Pack here. This is an Arctic heat pump. This is from Canada. AirMech, again, distributed through Canada. It's actually an Italian company. Chiltrix, this is a Chinese built product. It's distributed, I think, through Virginia. And then the big show every year, the AHR show, air conditioning, heating, refrigeration show. This is the Super Bowl show, so to speak, of the HVAC industry. Last year, 2024, on the show floor, Weil McLean introduced their unit. Here's US Boiler. Hitachi, Viessmann was introducing their unit there. Skybel Eltron's actually had that for a couple of years. IBC boilers, Gree. So again, there's a lot of product out there. You can see similarities in the form factor. They all have coils. They all have either one fan or two fans. Sometimes that depends on what the capacity of the heat pump is. If it's a nominal 3-ton, 36,000 BTU per hour unit, it might have just one fan. If it's a 4 or 5 ton unit up around 48,000 to 60,000 BTUs per hour, it's likely going to have two fans. Most of these units today They have variable speed compressors. They have variable speed fans. They're pretty sophisticated in terms of the controls that are operating these. The fan speed can automatically change. The compressor speed can change as well. So, right.
Is this, this is the equipment that's available that's in the United States. Is it available at distributors today? Like if we went to Granite Group or FW Web, we could buy.
I don't know, like FW Web or Ari Michaels. I don't know what brands they have right now, but yes, it's available. It's not all direct to customer sales.
Ryan, are there any that you're seeing that are more ubiquitous than ubiquitous?
I think Space Pack has probably been out there longer. Space Pack has actually had air to water products in the market for probably 10 years, but they have evolved with the technology changes. Just trying to think of the ones that are up there. Chiltrix has been around for several years. Airmec has as well. I think you're going to see the major boiler manufacturers really starting to push that product too. And, if you think about it, they need to be relevant Weil McLean's been around for over 100 years, as Burnham has. And their bread and butter has been fuel oil and gas-fired boilers. And they've built good products, but to face a market with, mandatory electrification and so forth, they need to have skin in the game. And so they have partnered with other manufacturers. Many of these products are coming out of China. You can go to China. We could form a company right here and go to China and get a new brand of heat pump from one of two big companies over there. There's a company called Medea, and then there's another one called Phoenix, and they will build it, paint it any color we want. So, they're good products. They're good products, but again, tariffs, trade relations, all that could have a bearing on where the pricing on this goes. Now, as far as form factors and how are these heat pumps physically constructed, the most common one is called a monoblock. And I'm not sure where that term it's a European term, I believe, and that's actually the way they do spell it. But the thing to remember, this is a pre-charge system. It's a self-contained heat pump. You don't have to add refrigerant to this. There's no refrigerant line set from the outside to the inside like there would be with a ductless mini split. So conceivably, a plumber that can put two pipes onto this thing and run some electrical hardware out there can install this. There's no need to check the charge on this, assuming that the unit passed its quality control. Basically, when you have fluid flowing through it, power going to it, turn the switch on and it operates. That being said, one of the concerns that I have, and I think to develop a market that is going to be stable long-term, I think it's important that contractors or installers that have been involved with hydronics or start to get involved with hydronics, and they want to install monoblock heat pumps, they need to learn some basic refrigeration skills. Not to install the unit initially, but down the road, if there's an expansion valve that might have to be replaced, a filter dryer, if there's a leak, now they have to deal with the refrigeration system. Some of them are choosing to sub out that work to other refrigeration companies that can do it. Many of the heat pumps that are in the field right now are running on R410A refrigerant. That's changed as of January of this year. 410A refrigerant can no longer the manufacturers can no longer supply products with 410A other than to sell out their inventory. Anybody know what the new refrigerants are? There's basically two that are out there right now.
R32.
R32 is one of them. And there's one called R454B. And these are semi-flammable refrigerants, but they are lower global warming potential numbers, and they're mandatory. As I say, in terms of global warming numbers, 410A is over 2,000. I think the R32s are around 700 something. I've got a slide at the end that gives that. Anybody know what may be here in about 3 to 5 years for refrigerant?
CO2.
Well, CO2 is out there, and there could be some more CO2 units. propane. Not the propane that you burn. Well, fundamentally it is, but it doesn't have the odorant in it. Okay, it doesn't have that mercaptan, that rotten egg smell. But propane is actually a really good refrigerant. You can get
That's quite a bit already.
it is.
It's small Pepsi machines.
Yep.
Like smaller refrigeration.
Yeah.
Bases.
And to get it into the, major residential and commercial heat pump market, I think it's going to happen. Propane has extremely low global warming potential. It's 3. CO2 is 1. So
Once it's supplied,
what's that?
once it is supplied, it has a low global warming potential.
Right, right. So,
There's irony there going electric and having propane to charge.
well, yeah, and, but propane from a refrigerant standpoint, you can do about 170-degree water with a propane
Really?
refrigerant. Yeah, you can get higher temperatures with it. There's only one little problem with propane.
That it blows up.
Yeah, it's an A3 refrigerant. It's a highly flammable refrigerant. That's going to require some internal redesign on the heat pump. And I'll give you a good example of that. Most hydronic systems inside the building will have an air separating device. So if there's air bubbles in the water, that will capture those bubbles and just simply release the air into the building. So here's a scenario. It's unlikely, but it's possible. I'll say the probability is low, but it's possible. Let's say there is a refrigerant leak in a propane heat pump, and you have higher pressures than the water side. So you might have 200 PSI refrigerant. It goes into the water stream carries the refrigerant in, and there's an air separator inside the building. Can you finish the story for me? The air separator would vent the propane into the building. So what do you do about that? Well, you put the air separator outside. It actually goes inside the heat pump cabinet. And that's how the companies like Viessmann and Daikin and others that are manufacturing, by the way, propane is R290. So if you hear me say R290, that's propane as a refrigerant. The companies that are doing R290 heat pumps right now have internally redesigned the product, not only from that venting standpoint, but also they're isolating electrical components, and they have to have sensors in the unit that will detect the presence of propane, and that will shut the unit off. So it's not as if we're asking somebody to put a bomb in their backyard. There are ample precautions that if there was a leak, that it can be managed. And that's one advantage of actually having a monoblock heat pump. All the propane under normal operation stays in the outdoor unit. Okay, so monoblock, this is the common form factor that you're going to see initially in the market. Now, there is also what's called a hydro split. What a hydro split is a monoblock heat pump paired with some kind of an indoor box. And that box typically has a circulator in it. It has controls, it has valves, it might have an expansion tank. What the manufacturer is trying to do is minimize the on-site labor to put the system together. So instead of the traditional hydronic installer going to FW Web or wherever, buying all these components, taking them to a job site and then putting them together, the manufacturers are trying to do as much of that under a controlled, pre-designed, pre-engineered, pre-manufactured setup. So essentially it's just running pipe. We have piping between the indoor unit and the outdoor unit. Now this piping has a mixture of water and antifreeze. This is not refrigerant piping. Okay, that's why it's called a hydro split. And then there's piping to the water heater. There's piping that goes off to an air handler, off to a radiant floor distribution system. So that's the second form factor, hydro split. And then finally, we get to traditional, what's called DX or refrigerant split, where we've got an outdoor unit, an indoor unit, and these would be connected by a refrigerant line set. Now we have refrigerant going between the outside unit and the inside unit, like we have with a ductless mini split or any type of air-to-air heat pump. So again, this is not exotic, misunderstood technology. It's well established. So to install this, an installer would have to have some basic refrigeration skills. They'd need a vacuum pump. They need to pressure test the line set. They need, the vacuum pump. And then once that pressure test is done, inside here, there's a couple service valves, and the outdoor unit is supplied with enough refrigerant to handle typically 30 to 40 feet of refrigerant line set. If you're gonna go 100 feet with the line set, first of all, you wanna make sure the manufacturer allows that. And secondly, you're gonna have to add refrigerant. So there's enough refrigerant for a reasonable line set length. And once the refrigerant line set's in place, you open two valves and the refrigerant simply fills up the line set in the indoor box would be under a vacuum at that point, a very high vacuum, and the refrigerant simply goes through the system and you're ready to go. Now, the advantage of a split like this, a DX split, there's no water outside, which means you don't have to use antifreeze in the hydronic portion of the system. You can, but you don't have to. Typically with a monoblock, the manufacturer's warranty is going to be based on having antifreeze in the system. So those are the three form factors: the monoblock, the hydro split, and then the DX split system. And those manufacturers that I showed you earlier, the majority of them right now are selling monoblocks, while McLean is selling and Nordic is selling a split system. Some of the products that'll be coming next year are also going to be split systems. Performance. Now, this is where a heat pump is definitely different from a boiler. When we buy a boiler, it'll have a certain output rating, especially if it's an on-off boiler. It's rated for 75,000, 100,000, whatever that number is. With an air-to-water heat pump, the output, the BTUs per hour, heating capacity that you get, very dependent on two things. It's primarily dependent on outside air temperature, and you could see as the outside air temperature increases, you get a lot more output out of the unit. But it's also dependent on the water temperature that the heat pump is working. The lower the water temperature, the better. That's the best single sentence to describe performance of an air-to-water heat pump. The lower the water temperature at which the heat pump can operate, the higher its heating capacity. And if we look at the coefficient of performance, and just so I know, does everybody here know what I mean by coefficient of performance, COP? It's the efficiency. It's the output of the heat pump divided by the input. So the higher the COP, the better in terms of minimizing the operating cost of the heat pump. Well, you can see the COP is also pretty strong function of outside temperature, and it's also a function of water temperature. So when it comes to retrofitting an air-to-water heat pump into a hydronic system, anything that can be done to lower the temperature or to keep that water temperature in that system as low as possible is favorable to the performance of the heat pump. Okay. And in a nutshell, what are things you can do in an let's say it's a house, let's say it's got a boiler, it's got some thin tube baseboard, very common hydronic system. Okay, maybe the house was built in the 1960s, it's a ranch house. What are two things that you could do that would bring the water temperature down? Insulate, improve the thermal envelope. Insulation. That's the other one. So very good, you got them both. Let's go back to the thermal envelope. You could add insulation, you can reduce air leakage, you could change the windows. Anything that will improve the thermal envelope will bring down the load, and that will bring the water temperature requirement down. And there's a formula for that. I don't have that, but I will give you an example. Let's say there's a house that has 100,000 BTU per hour heating load. That's a pretty high heating. So 1960s ranch, 3,000 square foot ranch, it could have that 2x4 wall construction, you know, some air leakage and so forth. Not really a prize winner in terms of energy efficiency. If that required 180-degree water in the baseboard system under those conditions, and you could reduce the load by 30%, so from 100,000 down to 70,000 BTUs per hour, the water temperature would go from 180 at design load, now worst day of the year, down to 147. Okay, and the more reduction in load you can create, the lower the water temperature without changing the heat emitters, without starting to add additional fin tube or other types of heat emitters. Now, the other option, and you nailed it, anything you can do to increase the surface area of the heat emitter system. You could add baseboard, you could add panel radiators, you could add floor heating, you could add fan coils, anything that is making that distribution system into a better overall heat exchanger will bring the water temperature down. And the thing that we have found over the years, many times people think they need this high temperature water, maybe 180-degree water. And the boilers might be set for that, but quite often we find if we start turning that water temperature down, that house heats just fine. We've seen systems where they think they need 180, you could heat with 140, 145-degree water on a design day. And it really depends on how was that original system constructed. Did they just run the baseboard wall to wall without doing any calculations? Some installers done that, okay? Or has the house been improved from an energy standpoint since the original heating distribution system was created? Maybe somebody's added insulation in the attic when they've upgraded the windows. So don't always assume that with a baseboard system, you need 180-degree water. There are ways to determine that. You can do an energy audit on the building, find what that design load is, and then work backwards based on how much thin tube length you have as to what the water temperature requirement would be. But again, key takeaway, low water temperatures are better for the performance of the heat pump, okay? And that's just a little diagram. Here's the source of the heat, that's outside air. We can't really do much about the temperature of that. But the sink or the load where we're sending the heat by designing or modifying the hydronic system and or weatherization on the building, we can bring this temperature down. And anything that decreases this temperature lift from the outside air temperature to the water temperature that we need to heat the building, anything that decreases that improves the performance of the heat pump. Okay, so low water temperatures are absolutely key. Now, I mentioned a simulation that we did. This was based on some software that was developed as part of a project for NYSERDA. And I put Plattsburgh in here because you've got a similar climate to Plattsburgh. Maybe, are you a little warmer than Plattsburgh here? A little bit?
A little bit cooler.
A little bit cooler, okay. Plattsburgh was rated at 8,000 degree days at a -9-degree outdoor design temperature. So we took a building that is a 36,000 BTU per hour design load in Plattsburgh. We assume we want to maintain 70 degrees inside. We also assume that if you average internal heat gain over a 24-hour period, that it would average about 2 kilowatts. That would be body heat, lights, appliances, solar gain, anything other than the heating system that adds heat to the building. We can change that variable in the simulation, but the results I'm going to show you are based on 2 kW internal gain. We assumed a 60 gallon per day domestic hot water load, heated from 50-degree cold temperature to 120. And then we ran this simulation for several different supply water temperatures at design load. Again, design load referring to that coldest day of the year. So, again, some people are saying, well, if it's baseboard, it must be 180 degrees, but that's not necessarily true. What kind of a system could potentially operate with 100-degree water and design data?
In one slab system.
In slab. If you had a good thermal envelope and an in-slab system, 12-inch tube spacing, minimal floor resistance, good underside insulation, everything's good about that. You could potentially heat a building with 100-degree, that's bathtub temperature water on a design day, right? And we also, this is important, when you assume full, what's called outdoor reset. Outdoor reset is the idea that as it gets warmer outside, our system can go to lower supply temperatures to our heat emitters. So we might need, let's say, 140-degree water on a very, very cold day, a sub-0 degree day. But on a 30-degree day or 40-degree day, we might be able to run that same system with 100 or 105-degree water. And outdoor reset is a concept that's been around hydronics for a long time, actually dating back into the 1930s with capillary tube kind of controls. Yeah, Honeywell actually had a dual bulb outdoor reset control. Pretty creative mechanical concept there. But that's important because, again, outdoor reset control never overheats the water for what the building needs at any given time. So again, a mild day, milder water temperature, cold day, higher water temperature. And by doing that, we're able to operate the heat pump more hours at reduced water temperature and hence higher COP. So how does it all shake out here? Here's the range of supply temperatures that we needed at design load. And let's start with just these red columns. Here's seasonal average coefficient of performance. Let's exclude domestic water heating for now. We're going to include it in just a minute. But there's the seasonal average COPs of the heat pump, ranging from about roughly 2.8 at the low water temperatures up to about 2.6. Okay. And one thing I think I had it up here. Again, put it on. This is important. In this simulation, we did not allow the heat pump to go above 130 degrees. Anything required over 130 was supplemental heat. Okay. I thought I had that on the slide, but I don't see it up there. So based on that, there are going to be times, and by the way, this system, yeah, if you were using 180-degree water, that would be, again, if it was a minimal pin tube baseboard system, and we limited the water temperature from the heat pump to 130, and when required to keep the building warm, we allow the water temperature to go above 130, but any heat produced above 130 degrees had to come from something other than the heat pump. We're still getting about a 2.6 COP on a seasonal average basis. That's actually pretty good. Now, you might say, well, some of the geothermal heat pumps, they'll advertise, it depends who you talk to. If you talk to salespeople, they'll say, yeah, we could do a COP of like 5 or 6. Anybody here familiar with geothermal systems? Show me one in the field that's producing a 5 or a 6. Show me one in the field up here that's even producing a seasonal COP of 4. I'll believe you at about 3.5 or less, okay? We're going to get into that more, but keep in mind that geothermal heat pumps, the rating systems, for example, they don't include the power that operate the earth loop circulators. That's a big deal. That's a big deal.
Well, where do these COP numbers come from?
These come from taking the COP curves that, for example, I showed you in the simulation.
But from AHRI testing or something like that?
Right now, no. They are actually testing, they are testing to an AHRI 550 standard, which is for reverse cycle chillers. Right now, AHRI is working on an air to water heat pump standard, and it's desperately needed.
But it has some limitations, just like any other laboratory test.
It does. So if you take those numbers, now, one of the other things that I want to make sure you understand, this includes a D rate for defrosting.
Oh,
Anytime you have an air source heat pump, be it air to air, air to water, you're going to build up frost. And when you get the outside air temperatures below 45, for example, this morning up here, it's likely you could come out and find an air to water heat pump or an air to air heat pump with frost on the coil. And it will stop. It actually goes into cooling mode. So it's going to take heat from inside and use that heat to melt the frost on the outside unit. With an air to air, that heat has to come from the living space. It's got to come from somewhere, see? And literally it has to come out of the air in the living space. With an air to water, it could come out of a buffer tank, or if you have a slab that's being heated. And the bottom line is you'll never feel that. The customer will never feel that the unit has gone into defrost. Has anybody here ever been in a building where a ductless mini split has gone into defrost? Experienced it? You can actually feel cool air coming out. Sometimes they'll shut the fans off, the blowers inside unit, blowers off. Other times it'll actually blow cool air for a short period of time, maybe 5 minutes. It's got to get heat to melt the frost on the outside coil. Now, if we, let's see, percent of space heating energy supplied from heat pump, no domestic hot water. This is the percent of the seasonal heating energy in Plattsburgh for that house. Again, it's 36,000 BTUs per hour at -9. That's a fairly well insulated house. We're actually doing up, well, at least 100% here and then down to about 91% here. Okay, so you can see the heat pump is still covering the vast majority of the seasonal space heating energy. The higher the water temperature, the lower it goes. Now, the other thing you might see here says the heat pump is a nominal 4-ton rated heat pump, meaning 48,000 BTUs per hour. But keep in mind, when we talk about a 4-ton heat pump, it's only that 4 tons or 48,000 BTUs per hour at a very specific set of conditions. Okay, if the air temperature is lower than those conditions, it's not a 4-ton heat pump. It might be a 3-ton or a 2.5-ton heat pump. If the air temperature was warmer than those rated conditions, it might actually be a 5-ton output. So what the simulation does, it looks at all those what are called bins in temperature from minus, I think we started at -20, went all the way up to 80 in 2-degree increments. For every one of those bins, there's a certain number of hours in a climate like here or in Plattsburgh. There's a certain number of hours where the outside air temperature is, let's say, between 0 and 2. And under those hours, we calculate the performance of the heat pump. We calculate how much energy delivered. We calculate the COP. And then we do that for all those bins. And then we collectively, we integrate that to get what the seasonal COP is. Now, when you add domestic water heating in, the COPs actually go up a little bit, the seasonal average COPs. Anybody got a theory as to why that would be the case when we add load to it? And think about this. Space heating is during the heating season, right? From up here, from roughly October to maybe late April. How long is the domestic hot water season?
Year-round.
Year-round. So how good does an air-to-water heat pump work when it's 90 degrees outside in July? Really good.
So
Okay.
why does the capacity go down?
Part of that is, I'm trying to remember. I'm drawing a blank right now. Let me think about that. I'll get back to you on it.
It's interesting, though, that the COP would go up and not.
Yeah, COP goes up primarily because of the domestic hot water. It could be just the total amount of energy now. You know, we're including domestic water and spacing and energy, and it's still the same nominal machine. That's
Does it struggle worse on its worst full day if it's doing both?
Typically it's going to prioritize one over the other. Most of the time, if the heat pump from a control standpoint is doing domestic water heating and space heating, usually if there's a simultaneous call, it's going to shut off space heating temporarily. It's going
And
to
go with the water.
go with the water and then shift back over.
The same that a boiler.
Basically, yes. And some controls, you can toggle it back and forth every 30 minutes or whatever. Okay, but typically you don't want to take domestic water away from people, domestic hot water.
No.
People complain. And these are a couple graphs. This is just taking some data. We ran this for several locations in New York State, but you can relate to this, starting up here in Plattsburgh and then going down to Albany and then finally going down into the city of Brooklyn.
Just crushing it, bro.
Yeah, look at the average COPs. And remember, this model was not created to try to make the results look good. It was created to try to make the results look realistic. That's why I stress we include the defrost in there. There's times when that defrost would lower capacity by 14%. Okay. And we based that defrost on some experimental data that Carrier collected over the years. Here's percentage of space heating energy supplied. And again, you can see based on water temperature at design load. So it's relatively flat between 100 and 140 here. Okay, but then it starts to drop off as we get up into these higher water temperatures. Again, because the heating capacity and the COP are strong functions of outside air temperature. So again, is a nominal 2.8 COP on a seasonal basis good? It actually is pretty good. It's 280% better than an electric boiler, right? You look at it that way. Again, the geothermal market, and I'm not here to bash geothermal by any means. We've done geothermal systems, but the geothermal heat pump market, their sales is largely pushed based on high performance. Why would you go out and dig up an entire lawn and put up 4,000 feet of pipe in the ground and do this and do that? Why would you just do that if an air to water heat pump could do the same thing? Well, it can't. The geothermal system does have, on an annual basis, a higher average source temperature because of the piping buried in the ground. But if you look historically what's happened in North America with the heat pump market, and I can think back to the late 70s, early 80s, air to air heat pumps coming from companies like Carrier and Trane, York. They were very finicky devices. They were not producing exceptional results back then. That early air to air heat pump market, if the outside air temperature went below about 15, maybe even 20 degrees above zero, the heat pump just shuts off. Okay, they did not have things like vapor injected compressors that we have today. So the connotation that developed from that is that heat pumps, air source heat pumps can work if you're south of the Mesa-Dixon. You know, if you live in Virginia or Florida or Texas, an air to air heat pump will work, but don't try that in Burlington, Vermont, right? Because we have a much colder climate. That gave rise to the geothermal market. Geothermal heat pumps were actually conceived to try to get around the poor performance of air source heat pumps, early generation air source heat pumps, and they did, and they succeeded very well. And you know, geothermal is kind of I call it the darling of the HVAC industry today. If you read publications, trade publications on HVAC, most of the editors love anything that says that has geo in front of it. Okay, they love it. I write columns on Hydronics for magazines, and I work with editors. I can tell you, there's something about the magic of geothermal. So what happened was we had a market where the geothermal heat pump performance was up here, and that early generation air to air heat pump was down here. Well, what's happened is this: over the last 20 years, the geo heat pump performance has gone up a little bit like this. COPs on air source will come up much more. So I call that the COP gap. And that COP gap between geothermal and air to water has closed quite a bit over the last 20 years. And it's true on air to air as well. COPs of air source heat pumps in general have come up a lot because of better refrigeration technology, things like vapor injected compressors, microprocessor controllers, variable speed, and so forth. All that technology has collectively improved the air source performance quite a bit. Okay. A little bit over. If I get another 5 minutes real quick.
Yeah, and that will bring us to the close of.
Yep, and then we'll take a short break.
Okay.
So again, why do I think the North American market is poised for growth with air to water? Okay. First of all, it's a hydronics. What sells hydronics? What people want with hydronic systems is comfort. And a well-done hydronic system is unsurpassed in comfort. And not just radiant floor systems, although how many here have experienced radiant floor heating? Yeah, they're pretty, when they're done right, and that's a caveat I have to put in there. If you take tubing and staple it to the side of the floor joist, it's not going to work, okay? But a properly done system is superior comfort. So we talk about comfort, I throw up this idea of BTUs in a box. Okay, so you've got this thermal envelope. I don't care what it looks like, all right? But it's got insulation, it's got windows, doors, air leakage, and so forth. And there's always heat leaking out of it, right? When it's cold outside. Well, thermodynamics says if I can put BTUs into the box at the same rate that the BTUs leak out of the box, the indoor temperature is stable. So if I just replace it at the same rate that it's being lost at, thermodynamics is satisfied. But thermodynamics doesn't guarantee comfort. Okay. Human physiological comfort is a pretty complex thing. And there's people that have done a lot of very detailed studies on it. It's not just about air temperature. Okay, anybody here ever been in a building? Well, we can use this building. Imagine it's 10 below zero and I'm standing in a t-shirt about a foot away from that window right there, right? I'm in a t-shirt, but it's 70-degree air inside and I'm going to be there next to that window for 3 hours. And it's, by the way, it's -10 outside. Am I going to be comfortable?
No.
Why not? 70 degrees around.
From what I do.
Well,
Surface temperature.
surface temperature, very good. Your body loses about half its metabolic heat output through radiation, thermal radiation. So that's a perfect absorber of thermal radiation under those conditions. So there's a lot of things that come together to great comfort. And again, if thermodynamics, yeah, we've got an energy balance between heat going out, heat coming in, but that doesn't mean we've got comfort. So I put down here, BTUs delivered except during defrost. Okay. I put this down here. Anybody know what these things are called? Hoodie footies.
Footy footies.
Hoodie footies. Should you have to put on hoodie footies to sit in your living room at night and watch a movie?
You have a problem.
That's right, you have a problem, okay?
Christmas morning.
Yeah, that's probably when you're gonna get them. But again, I'm picking a little bit on these ductless mini splits here. They put BTUs in, they do this, okay? But do they really give you comfort? And when I say comfort, there's thermal comfort, there's acoustic comfort. Okay, you might have somebody that's hearing impaired, they're trying to listen to their television or whatever, and you got that fan running, okay? You also have heat loss outside. We saw a system, we did a rough calculation based on refrigerant temperatures and how much line set was outside. That system was losing 5,000 BTUs an hour, just in the outside piping, before any of that heat got inside the building. Comfort when you're doing something with a combination of convective and radiant output, you do get better comfort because you have a better match to human physiological comfort requirements. There is a science to this, and if you want to delve into it, there's a fellow named Robert Beam that I've known for many years up in Canada. He's got a website called healthyheating.com. And Robert is world-class guy on human physiological comfort. And he's looked at, you name it, all the different factors of acoustic comfort, thermal comfort, how humidity affects it, how air movement affects it, and so forth. But in general, hydronic systems have an established reputation for superior comfort when they are done correctly. So that is the motivator. Now, I say that I'm an engineer. When I get involved with hydronics, I get very excited about things like cross-linked polyethylene tubing. And everybody knows what that is, right? PEX tubing. How about variable speed injection control? All that stuff, okay? All the technical stuff, in the weeds technical stuff. And I finally realized that most homeowners, you know, if I would sit down with homeowners and I talk to them about cross-linked polyethylene tubing, and you can have a variable speed injection mixing system in your basement. And I'm not degrading the homeowners. It's me that's the problem. I'm talking about the technical side of this stuff. What do they want from that system? Why do they want to spend, pick a number, $20,000 to put a hydronic heating system? They want to be comfortable, okay? And that, we can never lose sight of that. Comfort is the number one reason that hydronic systems are out there, right? Now, again, what's going to affect the market? Well, the market is very dynamic, I guess is the way to say it today. You've got electrification, changing policies regarding fossil fuels, changing consumer attitudes, net zero construction, and obviously, get a lot of offerings in hydronic heat pumps. So you put all that in a bowl and start stirring it. I tell people, put the politics aside, okay, contractors in particular. Put it aside and look at the opportunity that is being created out there. It's a huge opportunity. It's probably in my career, 40+ years, this is right now is the best time to be involved with hydronic heating systems because of the opportunity that especially heat pumps are bringing into the market. Quick example. Anybody here got a boiler that does cooling? Boilers don't do cooling, right? But heat pumps do. One of the things that has always been a detractor for a consumer in terms of making a decision on hydronics, what do I do about cooling? And I've seen this happen. People get excited about things like maybe it's radiant floor heating, but what do I do about cooling? Well, Joe, the contractor might say, well, I've got a buddy that does that. Here's his card. Talk to somebody else. Partial solution. It's like taking your car in for service and saying, well, the radio isn't working. Well, we don't do radios. Go down the street and, somebody else will fix your radio. That's not good enough. So with heat pumps, we can offer space heating, cooling, domestic water heating, and I'm going to throw a fourth one in there that's not really dependent on the heat pump, but it's heat recovery ventilation. I would advise an installer today that wants to work with air-to-water heat pumps and hydronics to learn heat recovery ventilation, learn how to install it. You can probably do programs, right? I'm sure heat recovery ventilator systems are being used, right? Passive house projects, net zero projects. So that allows that installer to offer a complete one source solution. By one source, one company dealing with all aspects of HVAC. Anyway, it does require some rethinking in the market. And in the hydronics market, like many markets, the hydronics market changes slowly. And when we see new technology come in, literally, it takes 10 years for the majority of the market to really embrace it, understand it, learn it, and apply it. You'll get early adopters like you will with other technologies, but then you'll get the people that say, I'll do it as long as my dad did it, his dad before him did it. Okay, you've got people that are resistant to change. And, that's their prerogative, but they are going to slowly but surely fade away as heat pumps become, I think air-to-water heat pumps could very well become the dominant hydronic heat source in North America. I won't say it's going to happen this year or next year. It might be 5 years, it might be 10 years. It's going to depend on a lot of the stuff that's up there. What is the government energy policy? What are rebates? Are rebates going to stay? Look at what's happened with geothermal rebates. Everybody knows what's going to happen right at the end of this year. Those federal incentives are going to go away. Now, you might agree with that, or you might disagree with that. But the point is, if you've based your market, if you've based your business plan on incentives, and incentives come and incentives go, it's a very unpredictable situation. Yes.
Utilities deal of hydronic water, it has a real limit for, say, the existing housing market in North America. It's pretty low, but we're not all that well insulated. So if they can only put out 130-degree water without a much bigger investment in temperature, then they're really not doing a great job. Whereas if you get this fancy possibly boiler that's beyond 92% efficient, and solve that problem, then what they would be water out of it.
Well, it depends on your distribution system and your heat emitters. I can show you buildings, we can heat them just fine at 100 degrees, 105-degree water. Well, yeah, they're not.
For our existing housing stock, both of the apartments and single family. Pretty poorly insulated.
In Vermont.
Yeah.
Yeah. I will tell you, start with the low-hanging fruit, and that is weatherization. It's pointless to me to invest in an air-to-water heat pump on an energy hog building. It's pointless to invest in a high-efficiency boiler or any other heat source if you've got, a significantly lousy, a very poorly insulated building. Put the money into getting the weatherization done first, and then size the heat pump to that. So. Yeah, that's going to be part of the challenge, but it's also, I mean, it's not that different from putting an ductless mini split in.
Oh, I agree.
Right.
They're not necessarily.
Right. So, yeah, if the building is leaking, get that, taken care of. Anyway, I don't want to delay too much here, but I'll go through these pretty quick. The growing interest in net zero right now. Okay, you're going to have typically photovoltaics, generating electricity, net zero, metering, or some type of metering that is going to allow some of the energy generated on site to operate the heat pump. Okay. Do you have net metering up here? Is it true net metering? Rate going in, it's the same as the rate going out of the meter?
No.
No, okay.
As therein lies the problem.
Well, yeah, that'll be part of it. I just was looking here, at some projections, compound annual growth rate, is between 2024 and 2030. It's projected to be about 17.5%. This is the fastest growing segment in the market right now, as far as construction goes. And the air to water heat pumps could very well fit in with net zero construction. Kind of related to that decreasing heating loads, where you can get buildings, when I started working, we routinely would have buildings that would lose at design 30 to 35 BTUs per hour per square foot. Today, you can design around 10, or some cases with passive, even less than that. So at, an 1,800 square foot building at 10 BTUs per square foot, 18,000 BTU per hour design load. This is one boiler manufacturer's offering. The smallest model is a 51,000 BTU per hour boiler. Now, yes, it can modulate down, but it's definitely overkill for the space heating needs of the building. So decreasing loads, again, allow heat pumps to be, a more active solution. Basic service charges on gas. You sell gas? Just electricity. Okay. And I just picked some bill here, $20 a month for having the gas meter on the house. So again, if you look at that, $20 a month, $240 a year just to have the gas meter there. If you can eliminate natural gas, you eliminate that basic service charge. And in some cases, the gas usage could be, the price for the gas usage could rival what that basic service charge is. It might even be less. Okay, I put that up there. Oftentimes we'll see with apartments or condominiums, you see this whole rack of gas meters. You see that up here too?
Oh, yeah.
And if that was hydronically heated, that could be done with BTU meters. BTU meters will actually allow measurement of the thermal energy that goes into an apartment. And it's all based on two things, flow rate and temperature drop. You know, the flow rate and the temperature drop, the meter can integrate that, literally second by second. And the meter will show how many BTUs have gone in. And this is widely used in Europe. Instead of having separate gas meters and separate, separate fuel supplies and combustion appliances in each apartment or each condo, they use district heating.
So is the property owner recovering the cost from the tenants?
Yes. Yeah. And this is where, and honestly, this, I don't know exactly what the laws are regarding this. Okay. Let's say you own a 10 apartment building and you put heat metering equipment in. Is there any law that prevents you from collecting for the thermal energy that goes into each apartment? Okay. So again, that technology, there's many companies that have heat metering that's out there. What that would allow you to do is put in a central plant. Typically, it's going to be 2 or 3 boilers. So you have redundancy and you have staging. So you can control the amount of heat generated. And then there'd be a distribution system through the building and a point at which there's a pipe going in and coming out of each apartment. There's temperature sensors, and the equipment that is sold for this, those temperature sensors are actually protected with lead seals, like an electric meter. So a tenant can't just say, well, I'm going to pay a little less this month. I'll pull the sensor out of the well. Okay. And there's a flow meter. And again, flow times delta T or flow times temperature drop is the rate of heat transfer. And you integrate that moment by moment over a billing period and you come up with bill based on it. Anyway, by eliminating gas, you eliminate the basic service charge. Here's another one, just the liability. Again, do you see buried fuel tanks up here, fuel oil tanks? Okay. A leak in a buried fuel oil tank is catastrophic in terms of environment and in terms of cost to clean it up. So there's a tank being removed. Okay. And now again, we design a lot of systems around fossil fuel boilers. And if you do it right, the safety is good, but you are generating carbon monoxide. And when you do things like put plumbing PVC pipe for venting a ModCon boiler, and I won't ask for a show of hands on that, that is not a good idea. That pipe is not rated for that service, but people will go to a Home Depot or a Lowe's, they'll buy Schedule 40 PVC pipe that's rated up to about 140 degrees, and they'll use it to vent a boiler that at times could put out 200-degree vent products. And people have died because of that. The piping or the solvent well that holds the joints together has failed. Here's a case. This is a 6-month-old galvanized steel vent connector. It's got a rust hole right through it. That's because the boiler was operating with flue gas condensation. The water vapor being produced in the combustion was condensing in the chimney and dripping down, and that's an acidic solution. And it just ate right through that pipe. This is the same thing. This is a scaled up heat exchanger in a copper tube boiler due to improper operation. These boilers like this are not intended to operate with what's called sustained flue gas condensation. I don't want to deviate too far, but these issues, whether it's buried tanks or venting carbon monoxide, they simply go away. Leave them. Now, the geothermal industry, that has been a roller coaster, magnificent roller coaster over the years. At the end of 2016, the initial federal tax credits of 30% expired. They were in place for 8 years. They expired. And during the subsequent 2017, the market went down by 50%. Now, somebody just took 30 cents on every dollar away from you. The market went down substantially. And then back in February of 2018, remember, this thing was passed, this omnibus spending bill. And somebody in the 11th hour slipped another sheet into the 2,000 sheet stack that said, reinstate the geothermal tax credits. And it went through. So the tax credits went back in place. And then this happened. This is how they were supposed to be phased out. Okay. So by 2024, they were supposed to, those retroactive reinstated credits were supposed to phase out. And then along comes this, the Inflation Reduction Act, which extended the tax credits through 2000. I think that should have been 2032, I believe, not 2034. But it was a 10-year extension. What happened to that? This is where we're at. Again, I'm not saying agree or disagree with this. I'm simply saying the market is all over the place as far as long-term business planning with geothermal. And I know people that work in the geothermal industry. This is not going to be a good year for them.
Well, this year will be.
It should be. Yeah, they should be selling like crazy at this point before December 31st. Okay. But
Solar too, right? Solar
yep,
needs-
solar, any of the renewable credits. But when you look at inflation, when you look at tariffs, all this stuff is kind of creating the perfect storm right now. I think it was 2 weeks ago, Carrier reported that their Q3 earnings were down 40% residential over the previous year.
Ooh.
It wasn't just Carrier. Train reduced substantially. This fall is not showing great results for anybody in the HVAC industry. And it's a combination. It's not just tax credits. it's all the other stuff, just the general inflation, mortgage rates, tariffs, so forth. But anyway, that's the question. If you're building a business, you want to build based on the assumption of perpetual subsidies. And no, I would advise you, no, you don't want to. Now, Vermont subsidizes, right? You subsidize air to water. New York State had a program that started March of 2024. Massachusetts has a subsidy, and I think there's a subsidy in Minnesota. I don't know exactly what it is. And that's good, but it's temporary, right? The thing that I like about air to water technology or the air to water market is that I think it can succeed without the subsidies. It has for several years. And if you look at the US as a whole, there is no federal tax credit on air to water heat pumps. Some states have it, some utilities have it, but it's not subsidized to the extent that geothermal is subsidized. Geothermal systems are inherently a lot more expensive to install, especially vertical borehole systems, okay? And people ask, well, how much less expensive would air to water be? And, you know, it's like saying, you can buy an Audi or you can buy a Chevy. What's the price difference? Well, tell me what the model of the Audi is and tell me what the model of Chevy is, and then we can go figure that out. But I would say in general, 40 to 60% of whatever the geothermal system would cost is reasonable pricing range for air to water. Because what goes away with air to water? That's a really expensive part of geothermal, the earth loop, okay? And say vertical boreholes in my area right now, about $3,500 per ton. And that's just the outside work. So again, geothermal is a good technology. It works. We've designed several systems, but it is an expensive technology. And what you need to look at is not just COP. You need to look at return on investment. Right? Just site disruption. Now, you know, let's say somebody's got this as their backyard. Maybe they own all this. Maybe they own the 25-ton excavator there too, right? Yeah, they can dig the holes and put the pipe in. But how about this? Should the cost of restoring the disruptive landscape be included in the cost of the installation? What do you think?
Sure.
I think it should. Okay.
Just see a lot.
I mean, as a contractor, you're gonna put the pipe in here, throw a little dirt on it, and say, now homeowner, you can put the grass seed on it.
We see a lot more of the well type geo systems than we do digging the hell out of our
Yeah.
yards like that.
Yeah.
Where do those from? Because what do you have with the frost? Those are not even down 4 feet.
Yeah, that's not us. I don't know what that is.
Yeah, this is deceptive. The finished grade's way up in here. This trench has actually been dug out.
Well, I know the Europeans love this idea, but like in Vermont, you see a lot more well-driven systems.
Okay.
The injection, rejection type.
Oh, open system.
Yeah.
Yeah. You have the water flow.
Door closed, like BGS, our
Okay.
sister company loves closed.
Okay.
We like open, but for colleges and stuff, you're not gonna see us digging up their yards.
No.
But it-
No, they don't have the space that they would need for the tonnage.
Right.
So anyway, it's simply the way it is, the cost of doing geothermal. And you know, if you've ever watched the wells being dug, the tailings that come up out of the well,
Yeah,
you don't just rake that off and
no,
throw
it's
some grass
pretty,
seed.
it's pretty nasty.
It's
Yeah.
very nasty, yeah. It's got to be trucked off site. There's
Yeah.
a lot of logistics that go away when you're not doing this. And of course, space-wise, you know, I just put, if you were trying to do geothermal, could it be done? I've seen geothermal systems in Georgetown, right outside of DC, in backyards they're half the size of this room. And they take the well drilling equipment apart, they get it in there, they put it back together. We call it cocktail geo. Because the people that are doing that, and they're spending crazy money, and I mean $200,000-300,000 to do this. They're doing it because they want to say, I have a geothermal heat pump system. there is no way that that would ever have a reasonable return on investment compared to other options. So when you have high density buildings like this, geo became, I won't say it's impossible, but it becomes impractical. Water heat, domestic water heat. Okay, as you reduce envelope loads down, your domestic load becomes higher and higher percentage. And an air water heat pump can do that. Ductless mini splits can't do that. Okay, and real quick, if you, real quickly, if you were heating with electric resistance heat, COP is 1. And I took a load of, where is it? 60 gallons a day, heated from 50 to 120 degrees. If you instead heated that with a heat pump at a COP at 2.5, which is certainly attainable, or even higher numbers attainable with air to water, and I based it on 12 cents per kilowatt hour, the difference would be about $270 a year. So using the using the heat pump for domestic water heating definitely would have a savings associated with it. And as I say, better insulated buildings, the domestic water load can become a higher percentage of total. So that's significant. There's a pumping. Now, I'm going to, full disclosure, I picked the one that had the 4 pumps on it. There are companies that make these pumping centers for geothermal heat pumps, and you can get them with 2 pumps, 3 pumps, or 4 pumps. But this is a product that they offer that's got 4 circulators. Each one of those draws 370 watts when it's running. So to pump the water through the earth loop, you're at almost 1,500 watts. And I want to show you what that does to COP. Okay. There is a standard, if you're looking at geothermal heat pump ratings, there is an ANSI standard. And there is a calculation for the wattage of the earth loop. But I've read that standard in detail, and I can tell you it's not accurate. It accounts for the energy to pump the fluid through the heat pump itself, not the earth loop. And if you've ever done calculations on sizing up the pumps for earth loops, there's a substantial pumping power to move, 12 gallons a minute through 3,000 feet of polyethylene pipe. It's not one of the little zone circulators that you might be used to on a hydronic system. It can be substantial. And I won't bore you with a lot of numbers, but if we calculated, and this is data right off a manufacturer's sheet here, we calculated the COP of the heat pump based solely on the energy, the electrical energy to run the heat pump, and we excluded the circulator to run the earth loop. We get a COP of about 3.4. But if we included, and that's only 287 watts to run the earth loop circulator, all right? So the numbers you see now in red include the electrical input to run the circulator for the earth loop. We go from about 3.4 down to just over 3. So we've got about 11% drop in our net COP. And this is one of the things that I've had discussions with people on geothermal heat pumps. Do you include the electrical energy to run the earth loop? Well, that's not in this standard, or at least it's not accurately represented by the calculations in that standard. Is the owner going to pay for that electricity to run that earth loop? Well, you better believe it. So I feel it should be included in the net COP of the geothermal heat pump system. Okay. And here's another thing. I always tell people, especially people that get really excited about supposedly high COPs on geothermal. You show me a utility bill that has COP on the line. You don't pay for COP. What do you pay for? Kilowatt hours, right? So how does a higher COP actually translate into a savings in kilowatt hours and ultimately savings in dollars? Well, we did a comparison, and it's in Syracuse. I live about an hour east of Syracuse. Let's say it's a 36,000 BTU per hour load. Outside temperature at design is 0 degrees. We're maintaining 70 degrees in the building. Syracuse has about 6,700 degree days. And we ran some software. the estimated annual space heating energy use is just under 50 million BTUs. That's what an MMBTU is. And we ran some software for geothermal, and we got a projected seasonal COP of 3.28. And then we used 2.8 for the COP of the air to water. So yes, the geothermal definitely has the higher COP. So here's a formula. This is pretty easy to work with. If you're comparing two heat pumps and one has the higher COP and one has the lower COP, it doesn't matter what the heat pumps are, air to air, air to water, water to water. You just have two COPs. Okay. So the higher COP was 3.28. The lower COP was 2.8. And this is the total seasonal heating requirement. So the savings was about 2.6 million BTUs per season if we were to use the geothermal heat pump. And at 13 cents a kilowatt hour, that translates into just under $100 a year. Okay. And it, proportional, I don't know, what's the residential rate up here for standard? 20 cents. 20 cents. Okay, so basically it would take that times 20 over 13 and, you know, it's relatively small savings. And the question is this. Can thus $99 a year in this example savings justify the higher cost of the higher performing heat pump? If it was a geothermal system, you've got a $14,000 or $15,000 investment in that earth loop.
But it can still do it because the COP stays the same as the temperature changes, and your equipment's largely indoors as opposed to largely outdoors. So you get a longer usable life with the geo equipment than you would with the.
Yeah. I'll give you the indoor versus outdoor equipment. You should have a longer life on a geo. You should.
Especially in like New York or Vermont where it's brutal on the equipment.
Yeah, believe it or not, there actually are interior air to water heat pumps in Europe.
That I wouldn't be surprised.
Yeah, what they do, if you can imagine just a corner in the building, they will actually set the heat pump there, and there's two very short but large ducts with two outside grills. One brings air in, the other discharges air. So there's an air handler section on the top. And so it's an interior air to water heat pump. I love the concept. We don't have it in North America at this point. Okay, that would.
Like in Spain or Portugal, they probably have the climate to do that kind of thing.
Yeah, there's several European manufacturers that have that.
Whole day.
Yeah, if you want to check one out online, go to Hotjet, just Hotjet heat pumps. It's a Czech Republic manufacturer, and they actually build some really nice little interior air to water heat pumps for apartments. These little things just hang on the wall. They look like a Modcon boiler. And you see two little 6-inch ducts that come up out of the top and they go outside and then they angle away. So the air streams don't immediately mix. But anyway, how would you amortize a $10,000 plus earth loop at $100 a year? Okay, that's really what it comes down to. So again, I'm not here to bash geothermal. I'm here to say we need to be realistic in how we look at COPs. And this COP gap I described earlier, that is substantially smaller than it used to be with air source technology. And then finally, the boilers don't do cooling. And as I mentioned earlier, that has been a problem in the hydronics marketing for a long time. And again, we've seen systems where the hydronics company comes in, they do a nice job on the system, totally separate company comes in and installs a cooling system, and it gets very expensive. Now you've also got two companies involved. They meet at the thermostat, right? Who's responsible? Yes.
So this drought source, I'm under the impression that it scales well. I have this at a certain scale, and gets big enough, it starts to become cost effective.
Well, yeah, and you know, with the current situation where the single family tax credits are going away, the geothermal people are looking at district systems right now and commercial. Commercial credits, I believe, are staying in place. I forget, it's 25C or 25D.
We heard from one of the folks in the chat that they're gonna be in place till 2032.
Okay,
And for folks that are online, the question was related to the scaling of geothermal. So for larger systems, it does become cost effective.
Yeah, I know in New York, there's a lot of interest, there's a lot of interest with, district geothermal.
Vermont is also.
Okay,
Yeah.
so it's,
Downtown.
yeah, it's going to be a shift in kind of where the focus of the geothermal market is going to go. So yes, I would agree with that. So again, there is equipment, including things like pre-insulated PEX tubing. There's fan coils that have drip pans in them. That looks like a ductless mini split indoor unit, but it's hydronic. It's got a remote. It's identical other than the fact that instead of refrigerant going through the coil, it's water going through the coil. Or if it's a central system, this is a 3-ton horizontal air handler that's got chilled water going to it with 3/4 inch pre-insulated PEX. And it's got a drip pan. You can see the condensate drain in it here and so forth. So bringing air to water heat pumps into the market now allows that installer to offer heating, domestic hot water, and small scale chilled water cooling. And that's not even close.